Thank you, everybody, for staying until this last talk. I promise that I will keep it light. And let me thank Dennis and the rest of the organizers for putting together this great conference. This is joint work with Arvind Magesan at the University of Calgary. Is very preliminary and incomplete work, and in fact, it's the first time that we present it. So please share your any feedback, concern, and criticism. Is the right time to receive it. Let me start with the context and motivation of this paper. We know that that firms make investment decisions under uncertainty, and they need to form beliefs about the distribution of future demand, costs, or the behavior of competitors. And firms also have heterogeneous beliefs for multiple reasons. First, they may have different ability to gather information and to process this information, but also they may have different, very heterogeneous, they may be subject to very heterogeneous idiosyncratic shocks. And the stochastic process of these shocks can vary also importantly across firms. Despite these, the great papers that we have seen in this conference, is still true that the role of heterogeneous beliefs by firms in this case on the heterogeneous decision of these firms and the potentially heterogeneous performance of firms is an under-studied topic in economics, and in particular in structural econometrics. Typically, we not only assume rational expectation of some particular forms of learning, like Bayesian learning, that imply homogeneous type of beliefs updating. We also make strong assumptions about the homogeneity of the stochastic processes that of the state variables that firms or agents in general have. Okay. And in this context, the main goal of this paper is to use data on firms' subjective beliefs to enrich the specification of our model, by a structural model, by allowing for a richer specification of state variables, and also a richer specification of the stochastic process, more heterogeneity in the stochastic process that these state variables can follow. And we are, in principle, we are not going to deviate, or we are not necessarily deviating from the assumption of rational expectations. Our approach can be perfectly consistent with rational expectations, but we are going to use these beliefs data as an outcome data that allow us to incorporate richer specification of serially correlated unobservables. We are in the process of applying our model and method to a model of firms' investment in capital and in employment, using data from a very rare type of data set in terms of information about beliefs, that is the survey of business uncertainty that is collected and has been created by the Atlanta Fed, with a very strong collaboration from Nick Bloom at Stanford and Steve Davis at Chicago. It is basically the predecessor of the data set that Aureo was talking about yesterday in the case of Britain. It has, as you will see, it has many things in common. Let me be very brief about literature review. There are several papers in this conference that are closely related to our work. In particular, the work by Sen and Pantano was an inspiration for us, for our approach, in general, for for basically the way of thinking about this problem, though we are going to use a very different method to the one that Juan and Sen use. Also is related because we use very similar type of data to the work of Aureo, Kehler, and Van Renen. And also to a recent paper by Horacio, Manuel, and co-authors. It's also related, or there is a paper, surprisingly, though, the survey of business uncertainty has been there for now many years, and the people at the Atlanta Fed are very sympathetic with people using their data. You can have the data in your computer. Do not need to go to any specific place to work with this data. As far as I know, there is only one paper that has used this data for a structural analysis or to estimate the structural model. That is the paper by Barrero in the JFS. Barrero is a former student of Nick Dodd. Okay, for the rest of this presentation, I will talk briefly. I will introduce some feature of this survey of business uncertainty. I will present some basic descriptive evidence related to the beliefs data in this data set, and then I will talk about our model and method. We still have we have very preliminary estimates using the actual data. Then what I'm going to present today is just Monte Carlo study. Okay. Then the survey of business uncertainty is a monthly firm level data set with a standard type of information about the industry, the location of the firm, some broad measures of size, and then monthly data on three variables, basically: the revenue, the number of employees, and the capital investment. And then what makes this data set unique is that together with the actual values of these variables, we have data on the subjective expectations of the managers about these three variables: revenue, employment, and capital investment, 12 months from now. I will talk more in detail about these beliefs data. Which are the subjects of this survey? They are senior finance executives. They are mostly CFOs. The sample covers there is more recent data, but the sample that we are going to use is from October 2014 to July 2023. In terms of the coverage of the size of the panel, every year it has information about around 1,600 responding firms. It tries to be representative of the non-agricultural sectors in the US economy and of the whole geography of the United States, because the Atlanta Fed used this data to construct an index that is called the uncertainty index I will present some evidence about that later. Okay, and it tries to be representative of the US economy. This is just some general features of the data in terms of the geographic distribution of the businesses, the distribution by sectors, two-digit sector, the distribution by number of employees. And you can see there the distribution basically of the type of respondents. Around 70% of the respondents are CFOs, and then CEOs. That these are sophisticated individuals who know basically what they are asked. They know what is a probability distribution, and they have a good idea what one would expect of the uncertainty they are facing. And unlike many other data sets that they have only subjective expectations, this data set contains information about the distribution of each of these three variables. revenue, employment, and capital investment. Particular, these business managers are asked to provide for each of these variables 5 points in the support of the distribution and the probability of each point in the distribution that should add to 100. Okay. And for instance, this is the part of the questionnaire that asks the respondent to provide the actual value of revenue during this month, and also the value, the rate of growth in revenue for the last 12 years. And this is actual values. And then just after this, the respondent is asked to provide these 5 values, the lowest that are described as the lowest, a low, percentage sales growth. These are questions about the expected sales growth for 12 months ahead. And these are the 5 values that it has to provide. And then in the next window, they have to provide probabilities that add to 100 for each of these 5 points. Similarly, for employment, these are the actual values of number of employees and the number of employees 12 months ago. And these, again, are the number of employees 12 months ahead and the probability distribution. Okay? And these are the online, these responses are online. They are contacted by email. Okay, then let me provide some very simple descriptive evidence, basically 2 pieces of evidence on this, descriptive evidence on these subjective beliefs. For this descriptive analysis, I'm going to focus only on 2 statistics. Given the distribution, we can obtain the mean of the distribution of the variable based on this subjective distribution, that we call it the subjective expectation. And we can obtain also the standard deviation of this distribution, that we can call it the subjective uncertainty. Okay. Then the first fact is that these subjective expectations have a very high predictive power. Okay. I'm going to present evidence for at the aggregate for all the firms. We have this statistic at the firm level. But basically what we do is we estimate a vector autoregressive model for the monthly revenue, the logarithm of the monthly revenue of a firm. And this is a panel data model where we exploit the fact that for most of the firms we have long panels. Then we estimate this model allowing for firm-specific coefficients, both in the intercept and the slopes. And this is a vector autoregressive model in terms of the 3 variables, the revenue, the number of employees, and investment. And we also include here, these are industry time fixed effects, okay? And we estimate this model, and based on this model, okay, we obtain 12 months ahead predictions of the value, okay? And obtain what is the absolute mean, the absolute forecast error, okay? And obtain for this model what is the mean absolute forecast error at the firm level and at the aggregate level for all the firms, okay? And all the observations. And then we obtain this mean absolute forecast error using the prediction, the expectation given by the firm, okay? The true value minus the reported expectation, subjective expectation, okay? And we have that, and we calculate this mean absolute forecast error, both for log revenue and log employment. The subjective beliefs performs better than this highly parameterized model of expectation based on autoregressive model. And it does only a little bit better, but it does better. The managers do better than this model, it was very surprising to us. We obtained also this mean absolute forecast error at the firm level, average over all the observations of a firm, and basically, and also the mean average forecast error for each firm using this model, and basically represent this in a XY type of graph. For most of the firms we have that the subjective beliefs perform better than this model. Okay, there's a few firms that know, but for most of the firms we have that the mean absolute forecast error is better than the one provided at this point. Not for investment. For investment, the subjective beliefs seems that it's more difficult to forecast investment, future investment. It does a little bit worse than this vector autoregressive. Okay. Then these subjective beliefs have very high predictive power. Okay, that's what I would describe this result. The second is that the measure of subjective uncertainty, okay, this standard deviation of the distribution, it has also a lot of predictive power to predict the absolute forecast error in the future. That is, to predict actual uncertainty. Okay. Then we run a regression, very simple regression, of the absolute forecast error for every observation, basically the absolute value of the realized growth in sales minus the expected value of the sales minus the prediction. And we run a regression of this error on the subjective uncertainty that ex ante the manager has provided in his distribution. And we see that there is a very strong correlation between the actual error, actual measure of uncertainty, and the subjective uncertainty that the managers basically report in their beliefs expectation. Okay, again, this correlation is stronger for revenue and employment than for investment, but it still is substantial. Okay. These are the indexes that the Atlanta Fed constructs using this measure of subjective uncertainty, basically using these standard deviations from the distribution of beliefs. They use basically a weighted average of this aggregating over all the businesses in the sample, weighted by the size of these businesses. And they construct this time series, and they report monthly this aggregate uncertainty index. This is the index for the sales growth. Interestingly, you can see that it was very stable before COVID. Then it jumped abruptly during the COVID first COVID months. It started to decline, and then it has been relatively stable post-pandemic, but notice that it has been stable at a level that is higher than the pre-pandemic uncertainty. Okay, and similar pattern for the employment uncertainty index. Okay. Okay. Then what is the model and method that we propose? Very simple. Okay. First, we have a standard model of demand for employment and capital, dynamic demand for capital and employment by a firm, okay, with this Bellman equation, okay? Then every period T, the firms decide the amount of investment in capital I and the amount of labor to maximize this intertemporal profit function that includes today's profit, that depends on these state variables, and the future expected value function experience. Okay. Then the key issue is these beliefs here, or this expectation. The approach that we are going to consider can be perfectly consistent with the idea that these expectations that firms use are the actual probability distribution of the state variables. Okay. Principle, we are not going to challenge this. As I will describe later, as a byproduct of our approach, we can test this null hypothesis, okay? But in principle, we are not going to challenge this condition, okay? What we are going to do is we are going to use our beliefs data to obtain a richer specification of the model in terms of the unobservable state variable, okay? And the model contains these observable state variables, basically labor at previous period because they are labor adjustment costs, and capital at previous period because capital is a dynamic decision, investment in capital. And then there is a vector of serially correlated or persistent over time and observable, omega, that follows a Markov process. Okay? And this, in principle, may contain multiple unobservables. Of course, we expect that log TFP will be there, but other unobservables that can affect the cost of the inputs and the productivity of the inputs might be in this omega. Okay? We have also other unobservables that are IID over time. They are not persistent over time, and we are going to make parametric assumptions about the distribution of these unobservables. This other distribution is going to be non-parametrically specified. And then we have two types of outcome variables. The standard outcome variable that we have in this type of model is the revenue function, okay, or the revenue, the amount of revenue that given the inputs that the firm is using at period T, the revenue that the firm generates. And then what is new basically in this, the type of data that we use here is that we have also beliefs data, okay? These are outcome variables. These are variables that the firm, the manager of the firm reports every period. And then these V variables, we have that the superindex represents the specific outcome variable, revenue, employment, and capital investment. This is for observation IT. And U basically represent the particular point in the support of the subjective distribution that the manager provides. Okay? And we have 5 points U where we observe these beliefs. Okay? And what we consider is that this is the key assumption of our approach, is that these beliefs that we observe, that they are data, they represent the probability distribution of this variable 12 months from now, okay? And this is the CDF. We represent these beliefs in terms of cumulative distribution, conditional on the state variables of the model, but importantly, also conditional on the decision. When a firm, a manager report its beliefs, it already knows what is the decision about employment and capital investment that it will make this period. Then these beliefs are jointly determined with the current decisions at period T. Okay, then this is the information that the firm has at period T, which is the typical information set that we will consider in our structural. Okay. Okay, then what we are going to do from this equation basically is to consider a flexible specification for this relationship, okay, such that we are going to be able to back up or to recover this vector of omega using data from these beliefs and, of course, data on the observable state and observables. This is the key step in our approach. Recovering omega using data from these beliefs, okay? You need to? Very good question. In our, eventually you will see, I will be try to describe this in some detail. We are going to use a factor analysis where, or a principal component analysis where we could identify the number of these components in principle. But you can think that in our Monte Carlo experiment, we have been tricky and we have assumed that we know the number of components. We have not tried to identify. Yeah. But yeah, very good point. So eventually, when we invert this relationship, omega, we are going to treat it omega as observable. We will have an estimate, it's a consistent estimate, and then everything will become observable. We will have to be careful in terms of standard errors and everything, but this will be, we are going to claim that we have consistent estimates of omega, okay? Exactly. In the model, the decision maker is constructing these beliefs, given that he has, this is the information set of the decision maker at period T, of firm I at period T. He knows omega, okay? And in fact, you can interpret our assumption as something weaker, and that's why we will be able to test rational expectation. Because in some sense, we are not really imposing that this is the true probability distribution. All what we need to assume is that when constructing beliefs, the decision maker is using exactly this information, okay? And if he's using this, if these beliefs that we observe are a function only of these variables, then we will be able to recover this omega, okay? Even if perhaps these beliefs are not perfectly rational in the sense that they are different functions of these variables compared to the rational expectation belief function, okay? For a given omega, we have different probabilities exactly because we have different data points in the distribution. That is going to give us, in some sense, over-identifying restrictions, in some sense. It's going to give us a system of equations, yeah? Yeah. This is 12 periods from now, yeah? Oh, 12 months, so, yeah. It doesn't matter, in principle, it doesn't matter if this is the information that you have at period t. It doesn't matter if you are asked about 1 period, 2 period, unless you have some, yeah, unless you have some information today that is only relevant 12 periods from now, but not 6 periods from now, because you know that a policy will be implemented after 12 periods, but not after 6 periods, things like that. But under a standard type of structural models, we will have that if this is the information that you have at period t, your beliefs 1 period, 2, 3, any periods from now is a function of your information set today, okay? Of the same information set today. This function will be different, of course, depending on what is the number of periods ahead that you consider, but it's a function of the same variables, the information that you have today. It cannot depend on any other thing that the information that you have today. Sure. I'm not sure if I understand what you mean, but let me say something. Basically, I think that we are going to avoid that problem by recovering the omega. Everything will be easier because once we have recovered omegas, now we are in the situation of a standard structural model where we can, given the state variables that we observe, we can construct the transition probabilities of 1 period ahead, and given the transition probabilities of the state variables 1 period ahead, we can construct any period ahead transition probabilities, no? Okay. Then the key issue is how to model this probability, these beliefs, okay? Then we have tried to have a compromise here between something flexible, but something very easy to implement, okay? And basically, that is the function that we have used so far. It can be described, we could describe it as a factor quantile regression model with endogenous regression, okay? And there is basically a transformation of the distribution. Here is a logistic transformation of this CDF, okay? That is a linear function of the information, okay? Of the observable decision, the observable state variables, and the unobservable factors that we do not. But this function, of course, depends on the variable that we are considering. It depends on the particular point or quantile, if you want, in the distribution of the variable of the beliefs. And these parameters, and here we are exploring the fact that for most of the firms we have a long panel, it is firm specific. Okay. Okay. Then this is a relatively flexible model. Still, we have an important complication here, and notice that we have 12 equations. Basically, we have the same explanatory variables and the same unobservables in for all the 3 outcome variables. But we have 3 outcome variables, and we have 4 points U. Okay, then 4 times 3, we have 12 equations here. Okay. But we have a serious endogeneity problem. Basically, all the observable variables are endogenous here in this regression. Current employment, current investment are a function of the current and observable state variables. And because omega is serially correlated, they are also correlated with previous employment and the capital stock at the beginning of the period. And everything is endogenous here. Our approach so far to deal with this is just basically exploring the Markov structure of these unobservables. Okay. Then for the moment, what we have considered is that these omegas follow a linear vector autoregressive model that is firm specific. Again, this is a matrix of autoregressive parameters. Okay. And these are innovations. And of course, this is the innovation of this variable at period t plus 1, and therefore is mean independent of all the information at period t. It's mean independent, this innovation in the stochastic process of omega is mean independent of the decisions at period t and the states at period. Then combining this, basically, we can use this linear equation. We can plug in this linear autoregressive model here to basically transform this model in one where the error terms are these innovations, basically, which are orthogonal to, I call it the Cochrane-Orkut type of transformation of the model. Okay, it's a Cochrane-Orkut type of transformation where now we end up with a model where we have lagged values of all the observable variables and lagged values of this transformation of beliefs. But the resulting error terms are these innovations that are mean independent to all the information at period. Then basically we can estimate this model, the parameters of this model by OLS, basically. Okay, under this assumption. Okay, then this is basically the second step of Oli and Peikes in some sense. Okay, but here what we have is beliefs. Okay, then with our large T, we can estimate these parameters at the firm level. Okay. Then basically, what the estimation procedure, first we estimate the beta parameters associated with the observable variables. Given that we are going to have a residual for each of these 12 equations, but we know that this residual for these 12 equations, these 12 residuals are a function of, let me say, 4 omegas. And then now we have a factor model, okay? And using the factor model, we can estimate the variance of covariance matrix of the omegas and the beta parameters associated with the omegas. And then once we have the beta parameters associated with the omegas, we can recover the omegas themselves, okay? And that relatively standard factor model estimation, okay? Yep. That's right. Yeah, this has been trial and error. Basically, this is based on our experimentation with the Monte Carlo. Basically, we simulate, as you will see later, we simulate data from a structural model where we know which are the true omegas in the model. We simulate data from that. We obtain rational expectation beliefs as if they were the elicited beliefs, and then we are trying flexible models, okay, to try to basically see that they fit very well the belief data that we have generated. And this works reasonably well. But you could consider other transformation of the CDF that is not the logistic. That makes a lot of sense. Yeah, yeah, definitely. We, as you will see, the Monte Carlo that I'm going to present is performing relatively well, but not spectacular as in your case. Then there is room to try to improve basically in this, and this is the key part to try to improve the Monte Carlo performance and eventually the estimate. Yeah, sure. Definitely, there are zeros in investment. And for the moment, we are being very crude there. Logarithm of 1 plus investment. Yeah. And we are not, in the Monte Carlo experiment, we have not introduced zeros for investment. There is no fixed cost or sunk cost of investment. Sorry? Definitely. Yeah, we will need to deal with that. They are definitely zeros, as you know, substantial fraction of zeros in the data in investment, yeah, as well as in employment. Okay, then yeah, employment is lumped too. Yeah. Okay, then basically the estimation procedure is quite straightforward. First, we use this approach to estimate omega. We are going to get this omega hat point-wise for every observation. And then basically we plug in these omegas everywhere, okay, in our revenue function and in our profit function, okay, to have a rich specification of the model in terms of this serially correlated. And we can, of course, estimate the transition probabilities of this omega, okay? Then once we do this, the remaining unobservables in the model are only the IID type of unobservable, then we don't have endogeneity problems, and we can use pretty standard type of models to estimate this dynamic structure. Okay. Of course, it's important that we have consistent, according to our assumptions, consistent estimates of omega hat. There is an estimation error, okay, and we need to account for that to construct confidence. Okay. As I mentioned before, the key restriction really that we are making is that the beliefs that firms elicit are deterministic function of the same variables as the true beliefs. Okay, but we are not assuming, though they are deterministic functions of the decision and the state variables of the model, we are not assuming that they are the rational expectations. Our procedure at any moment imposes the restriction that these are rational expectations. Then once we have estimated our structural parameters of the model, we can construct from our model, okay, what is the probability distribution of these in the data. In fact, we can do it even before estimating our structural model. Once we have estimated the omega in the first step, we can construct basically these probabilities, okay, from the data. And we can compare it with the belief data, and that will give us a test for rational expectation. Okay, Monte Carlo experiment. Very standard model of demand for labor and capital. Profit is equals to revenue minus the cost of labor minus the cost of capital. The revenue function is Cobb-Douglas, and we have two unobservable, the log TFP, but also the elasticity of revenue with respect to labor and capital. There is an unobservable here. We impose constant returns to scale. And then the cost of labor, it has the adjustment cost of labor, it has a linear component and a quadratic component. And the coefficient associated with the quadratic component is also a time variant serially correlated state variable. The same for the adjustment cost of capital. And we have 4 serially correlated and observable here. They follow a vector autoregressive model of order 1. with firm-specific parameters, and basically these 24 parameters in the vector autoregressive model, they are random draws of a uniform from uniform distribution. Okay, random draws, but time invariant, of course. They are okay. Then we simulate data for 1,000 firms during 60 months. We solve the dynamic programming problem. We generate data, and using basically we generate the belief data from the rational expectation beliefs. Okay, in this. Then basically this is the result of the first step. This is the a figure where in the horizontal axis we have the percentiles, different percentiles in the of the true log TFP, and in the vertical axis we have the recovered or the estimated log TFP. Okay, these are box plots. The closer are the box plots to the 45-degree line, the more precise are our estimates of these unobservable. And for log TFP is quite good. This is an R square of 95%. Similarly, with some bias, some attenuation bias here, we have also a high R square for the elasticity for revenue with respect to labor. Okay, things are not so good, and we need to explore this further when we go. The R square are also relatively high, but there are systematic biases here for the unobservable in the adjustment cost of labor, and also in the opposite direction for the unobservable in the adjustment cost of capital. There are substantial room for improvement here. Despite these biases, in some of these biases, the estimates of the transition probability, the autoregressive process of the vector autoregressive model, these are the true parameters, these are the estimated parameters, they are quite precise, very little bias. These are the estimates of the structural parameters, these are the true structural parameters, the average values of the intercept in the production function, the slope parameter, and the adjustment cost. You can see that there are some biases, but most of the biases are in the quadratic adjustment cost of the capital and labor. Still, I think that my interpretation is that the results are encouraging, but we need to improve basically our specification of this reduced form model for the subjective belief. Okay. So basically, we are using this new type of data of subjective beliefs of firms in a very rich way, using this distribution to basically try to enrich our specification of serially correlated and observables in dynamic models of firm behavior. And we are looking forward to present results where we include the empirical application. Okay? That will be next time. Thank you.